Hey everyone, welcome to Mr. Winter's chemistry videos. I'm Mr. Winter. Today we're going to be talking about mole conversions, specifically how we can use molar mass to convert between the moles of a substance and the mass of the substance, hence molar mass. Today you're going to need your calculator, periodic table, and don't forget I've linked below a graphic organizer which is following along with the questions today. So let's go ahead and get started. Um, Generally speaking, when we're thinking about moles, molar mass, and even Avogadro's number of particles, stuff like that, we want to be really comfortable with how we can convert between these things, how we can convert between those things. So the first thing that I want to start with is really just kind of understanding the conversion factors between particles, moles, and mass. And really the mole is going to be the heart of chemistry. It's the center of chemistry. So we're going to use two conversion factors today that allows for us to convert in and out of moles. There are like literally tens more, maybe even hundreds. I don't. So let's go ahead and check it out. We're going to look at the particle to mole, and mass to mole. So if you remember, we talked in the first video about Avogadro's number. And Avogadro's number is 6.02 times 10 to the 23rd particles per mole. Basically, it allows for us to convert between moles and particles. Now, if you're trying to think about what particles are, particles will be atoms. That's a really common one. In AP chemistry, we often talk about the particle of a photon. It's not quite a particle, but it is a particle. We'll get there later. Molecules are particles, etc., etc., etc. Compounds, formula units, just anything that's small is going to be a particle. So if I want to convert between moles and particles, I use Avogadro's number. And today, once again, we're going to be focusing more on molar mass. Molar mass could be found using the molar masses from the periodic table. For example, carbon's molar mass is 12 grams per mole, 12.01 grams per mole. The units for this, once again, are grams per mole. So it allows for us to convert between this unit of mole and mass, and the units for mass are going to be in grams. The units for mass are going to be in grams. So here's our map here. I generally like to tell students, like, hey, if you have to memorize this, the first thing you should do on a mole conversion test is like write this on top of your paper. Write this on top of your paper. So let's go ahead and move on here. We're going to go ahead and check out our first practice problem here. How many atoms of gold are in a 10-ounce gold coin? The gold coin is going to be 24 karat gold, which is basically just telling us that it's pure gold. It is pure gold. Luckily, I don't have to do the conversion factor between ounces and grams because it's provided for us here. So we're just going to go ahead and get started by writing out the amount of gold that I have to convert, which is 331 grams of AU. Now, if you're looking at that mole map, you see that we're starting on the right-hand side, going from grams. And first, we're going to convert into moles. And the way we do that is using the molar mass. If you look at your periodic table, the molar mass for gold is 196.97 grams for every 1 mole. We continue this across using our dimensional analysis techniques. For every 1 mole of AU, so this is AU, this is our gold atom, we have 6.02 times 10 to the 23rd atoms of gold, atoms of AU. Multiply everything across the top, divide everything on the bottom. We find that we have quite a large number of atoms, which makes sense. 300 grams is a good amount. So 1.01 times 10 to the 24th atoms. AU. Excellent. Dimensional analysis can be a little bit tricky. If you need extra practice with this, you can find some videos online along with ones that I've made as well. So let's go ahead and move on here. We're going to go ahead and check out our next problem on the graphic organizer, which is this. On average, there are 43 quintillion, 4.3 times 10 to the 19th atoms of silicon in a single grain of sand. That's massive in my opinion. What is the mass in grams of the sample of silicon? So we were looking really for how much of that sand is this atom silicon. So we're actually going the other way now. We're starting at particles and moving our way towards grams. We're starting at particles and moving our way towards grams. So we're going to start with the amount of particles we have, the amount of atoms, 4.3 times 10 to the 19th atoms of Si. And once again, since I'm starting on the left-hand side and moving my way right across the mole map, I'm going to first use the conversion factor Avogadro's number. So I'm going to divide by 6.02 times 10 to the 23rd atoms of Si. And I know that for every 1 mole of Si, this is how many atoms I have. I'm going to continue with my dimensional analysis because I want the mass of silicon. And I know that for every 1 mole of silicon, I look on the periodic table and I find it has a molar mass of 28.09 grams, 28.09 grams. So multiplying across, dividing on the bottom, we find that our sample is actually quite small. And this makes sense, right? We should always play this game of, does it make sense? It's 2.01 times 10 to the negative 3 grams of silicon. And it makes sense. A single grain of sand is definitely going to be less than a gram. And as far as sand goes, it's not made of just silicon atoms. There are also oxygen atoms and sometimes even carbon or nitrogen in them. So we're going to go ahead and clear this up. We're going to move on to the next problem here. A sample of unknown substance contains 3.42 times 10 to the 24th molecules and has a mass of 125 grams. What is the molar mass of this unknown substance? So this is a little bit of a trickier one, really making sure we understand what the concept of molar mass is. If you look at the top of the graphic organizer, you'll see that I have provided us with an equation, if you will. I like to use this m with feet to indicate molar mass. And let's think about the units for molar mass. Units for molar mass are often grams per mole. So we have this formula here where it's the mass of the substance we're looking at divided by the number of moles of the substance we're looking at. If we can find mass and moles and divide those two values, we'll end up finding the molar mass. And luckily, we're already provided with the mass here. This substance has a mass of 125 grams. I do not currently have moles though. That's what's provided up here. So what I'm going to do is do a quick conversion factor. 3.42 times 10 to the 24th molecules. 3.42 times 10 to the 24th molecules. All I have to do in order to do this problem is divide by Avogadro's number, 6.02 times 10 to the 23rd, not 24, sorry about that, 23rd molecules. Is equal to 1 mole. A mole and a molecule are not the same thing. Remember, a mole is a counting number. So when I do this division here, I find that my sample has 5.68 moles. And now that I know the denominator and the numerator, I can go ahead and find that 125 grams divided by 5.68 mole. All I have to do is do this division, and I find that my molar mass of my sample is 22.01 grams per mole. So this molecule has a pretty small molar mass, but it makes sense. We can have molecules that have a small molar mass, as long as it's bigger than 1 gram per mole, because at the end of the day, the smallest element, hydrogen, has a molar mass of 1 gram per mole. You're pretty much okay. All right, let's go ahead and do the last problem on the graphic organizer. We're going to do the last problem on the graphic organizer, which is this one here. It's kind of a trickier application type problem, really making sure we understand what the concept of moles means. So what mass of CH4 molecules has the same number of molecules as 25.5 grams of CO2? So a good starting point for this problem would be to figure out how many molecules of CO2 I have. And the only way I can do that is by converting 25.5 grams of CO2 to moles. I know that the molar mass, by figuring it out on the periodic table, is 44.01 grams for every 1 mole of CO2. And this is where the next step is interesting. I actually kind of like this step. There was a conditional statement provided to us. I'm trying to find the same number of molecules. And so because of this conditional statement, I know that for every 1 mole of CO2, I'm going to have 1 mole of CH4. Now, I don't always have to have the same number of moles of these things, but because I'm looking for the same number of molecules, and because the mole is a counting number, I can go ahead and make this and state this step. Last but not least, I multiply out by the molar mass of CH4. So for every 1 mole of CH4, I know I have 16.05 grams. Multiply everything out and get 9.30 grams of CH4. 9.30 grams of CH4. Wonderful. That's it for today. Don't forget the graphic organizer that follows this is posted below. And have a great day. I'll see you next time.